Oh, this is really small. Let's see if we can get it bigger. I cannot see that.
Hold up.
That's a little bigger. Okay, that's kind of small, but hopefully we can see it a little bit. So we're deciding if it could form an ionic compound, and then we have to write the formula. So the first one is we've got potassium and magnesium. So potassium and magnesium. Will that form a compound? An ionic compound? No. Okay. Why not?
Because they're both metals.
Good. They're both metals. Won't form ionic. We need a metal and a non-metal for ionic. Perfect. How about sulfur and calcium?
Good, yes.
Good. So we have a metal and a non-metal. So then we need to, so we put yes, and then we have to write the formula. So what do we need to remember?
From left to right.
Okay, so left to right, yes. Metal always goes first in the ionic formula. So metal is first. What's the charge on calcium?
+1. No, +2.
+2, good. So the first column forms +1, second column forms +2. Calcium's in the second one, so 2+. And then sulfur, what charge is on sulfur? -2. So then we just need one 2+ charge for one 2- charge, so it's CaS. Okay. Next one, we have oxygen and rubidium. Would that form an ionic compound? Yes, we have a metal. This one's a metal and a non-metal. Good. So then we need to do the same thing. What's the charge on rubidium? Good. And what's the charge on oxygen? 2-, it's right by sulfur. Good. And so then metal goes first. Even though they didn't write it first, metal, you have to know metal goes first. And then we need 1 oxygen for 2 rubidium. So this is going to be 2 Rb2O, because we need 2 + 1 charges to balance the 2- charge. Okay. Then the last one is barium and iodine. Would that form an ionic compound? So, yes. Yeah, good. We have to be careful. There's some like barium or boron or bromine. We have to be careful. We make sure we're looking at the right one. So barium is a metal. Iodine is a non-metal. What's the charge on barium? And good. +2. What's the charge on iodine? Yes. So then we need 1 barium, for 2 iodines. So Bai2. Okay. How do you feel about that one?
How do you get like the last part? Like, so I know there's like a 2+ barium, but how do you know iodine is?
Oh, so the first column, or the very right column, the light blue one, is the noble gases. Those don't form any charges.
Okay.
And then fluorine's column has 7 valence electrons. To get 1 more, to have 8, they would get 1 electron. They'll form a -1 charge. So it goes -1, and then oxygen's column forms -2. The nitrogen's column forms -3 if it's a non-metal. Does that help? And that's, I would either write that on my note card or memorize that. Yeah, does that help? Okay, other questions? Okay, all right, let's talk about, so we're doing chapter 6 notes today. We're gonna do lab 3 on Tuesday, and then we're gonna come back and do lab 4 on Thursday. I have the labs so that the labs don't show up on a early out. So, because that would just not work very well for most of our labs. So we're going to look at the pre-lab quiz for lab 4. So I think that worked last time. We kind of went through it together. So if you want to pull up pre-lab 4, we'll talk about the lab for pre-lab 4. I'm going to find the modules and I'm going to open the instructions. Wherever the lab. Oh, there we go. I think it can make it bigger. Where is there we go. I don't know why modules are not page. Okay, so I'm gonna open lab for instructions. And we will need these as we go through. Okay, the first question says, what is the difference between beaker tongs and crucible tongs? So beaker tongs. Let's look at what a beaker tong looks like. Okay, so what do we know? Oh, we could buy some from Amazon. What do we notice about those beaker tongs? They have rubber on the end, yeah. Good. Okay, let's look at crucible tongs. That's what oh, you have them. Crucible tongs. We have crucible tongs in our lab. Hopefully we don't need beaker tongs. Okay, images. So what do you notice about crucible tongs? They don't have rubber. Great. So you can put that. They also have this like weird, this is where you pick things up mainly with those crucible tongs. So they pinch together and you can get a really good grip on the crucible and move it around. The beaker tongs are rubber. They have that rubber thing around the middle, or you can hold the beaker around the middle with those rubber tongs. Okay, what is the difference? Great, we got that. What is the warning sign? What warning is given in section on combination reactions? Types of reactions. Combination reactions. Do not look directly at the flame. That seems very important. Oh, good. So that part, you're going to, let's see. You're going to burn magnesium in this next lab. So that'll be great. But don't look at it. Don't look directly at it. Okay, describe which precaution you should take while heating reagent and test tubes. So let's see if it talks about that. Here. Is this searchable? Let's see if we can find it. Heat in. Let's find test tube. Set this aside. Observe. Does anyone see it? Ah, here we go. When heating reagents in test tubes, slant the test tube so the opening is pointed away from people. So that if it comes out of the test tube, it's not pointing at them. Heat the test tube at the surface of the material and work down towards the bottom. Do not heat the test tube from the bottom. So I'm going to draw you a picture of what they want you to do. This is lab 4 for next week. So you're going to tip your test tube like this. So your liquid level, there's like more liquid down here, there's a little bit of liquid here. This is where you're going to heat. This is your flame. Obviously it's a flame, right? Okay, now, does that look like a fire? And this is your Bunsen burner. Yes? Kind of thing. So you're going to heat right here in your liquid, and then you wiggle it around, so then your liquid will evaporate. This is how you get it to evaporate out of the test tube. Okay? So that's what it's talking about. All right, we've got that one, number 3. Okay, number 4, when doing a wooden splint test, what differences would you expect to observe between oxygen and hydrogen gas? So a wooden splint test is you have your test tube and you stick a glowing splint into the test tube and you see if the gas inside is reactive to the little flaming stick, okay? So does anyone know if oxygen or hydrogen are flammable?
No, hydrogen is flammable.
Hydrogen is flammable. Oxygen is also flammable. So we need to figure out how do they burn differently, because you should be able to tell if it's hydrogen or oxygen based on this wooden stick test. Let's see if they have that. Ah, here we go. So this is in the decomposition reactions. Towards the end of heating, light a wooden splint. Insert in the flaming splint into the mouth of the test tube. Note what happens to the splint. Oh, it doesn't tell us. Note what happens. Are they not going to tell us? What is this? Oops. Okay. I'm not sure if they're asking you to guess or to look it up. So hydrogen should react really quickly. It should make a pop. And oxygen doesn't do that. Let's just check. I think that's what they're looking for. Oxygen gas versus okay. When a burning splint is introduced to a sample of hydrogen, it will burn with a popping sound. So it should pop. Oxygen, when the splint is introduced, it should reignite. So you put one that's like going out. You put like one with a glowing splint, not a flaming splint, and the splint will relight. I think hydrogen just reacts a little bit faster, and so then it does its pop. I'll see if I can find a video of that for you for Thursday. Okay, I think that's what they're asking. I feel like they should tell you that. Okay, which type of chemical equation contains spectator ions? So in this, is this for Latin? Okay, let's see. Complete ionic equations show all the chemical species with ions with charges. So let's see. I think that should contain spectator ions. So the complete ionic equation, that one is going to give you everything. It's going to have all of the ions, even these ions that don't participate. Okay. So there's some ions in a reaction. We can look at this on Thursday also. Sometimes ions don't participate. They're just present to balance the charge. But they still show up. We write them in the complete ionic equation. Okay, number 6. Which type of equation contains no charges? So if we have the balance chemical equation, then we aren't going to write any charges. So that's what we were doing in chapter 5. We didn't ever write any charges in the chemical equation. Okay. And then the number 7, which type of chemical equation contains just the species that are involved? So this is called our net ionic equation. We don't put any charges in the net ionic equation. Okay. And then the flocking agent. Let's go back to our instructions. I saw it up here. Oh, background information. Okay. Flocculation is a process by which the colloidal impurities adhere to the precipitate. The resulting floc is allowed to settle to the bottom. So a flocculating agent is something that's going to grab onto the particles in the solution, or it's going to adhere to them, and then it's going to make it so that we can purify the water. So this is like for water purification. So it helps you precipitate out impurities by adhering to those chemicals. Okay. Oh, here it is. Flocking agents are compounds that contain both a cation and an anion. Okay. Well, I'm not sure what they mean. So something like that. And that helps us to precipitate the ions in the solution. Okay. Number 9, where should your chemical waste be placed? So let's go back to the lab instructions. The lab instructions have a little box at the end of the sections, and it says in the chemical waste container in the fume hood. So usually I leave a waste station at the table. So we'll probably do that. And then I can put it in the fume hood at the end. But you're going to put it in the chemical waste container. So watch for those on Thursday. Observations that read the solution changed to a blue color would be sufficient to provide all needed data. I don't know what they're talking about. Let's see. Description should include changes in color and or opacity. So it looks like they need more than, let's see, blue. I would guess that one is false, but I don't know. That's my guess. False. Let's try it and see. It is false. I only answered 2 of them, but okay. Questions for me? It looks like there's a few that I'm gonna have to go back and grade, and I'll work on that. Okay. 5.
That's what I had.
Oh, there's 5 that I need to go back. Oh, I thought you said you were asking about number 5.
Oh no.
Okay. Okay, there's lots that I need to go back and grade. Okay, let's go to our notes now. We're going to talk about chapter 6. We need to get through these last 3 topics. Let's go to Alex. There we go. And then chapter 6. So the next one we're going to talk about is calculating an equilibrium constant from an equilibrium expression. So do you remember we talked about, let me pull this over. Oh, do you need a minute to do that pre-lab, or we're good? Sorry, I didn't give you more time. We're good? Are you ready to move on? Okay. So last time we talked about the equilibrium expression. So we talked about the equilibrium expression or the equilibrium pressure expression. So remember when we're talking about this, what goes on the top? Products. Products go on the top. Products. And then reactants go on the bottom. So I think that's the most important. And then for this one, it's like the concentration of product A raised to its coefficient times the concentration of product. I guess usually we do like this. Let me fix it. So this is usually our product is C and D, and we raise those to the exponents. Does this sound familiar? And then we have concentration of A raised to the A times concentration of B raised to the B. So we're just going to use this, set it up, then plug in the numbers and get out a number, okay? So what we're going to do is we're going to set this up and then use the numbers they give us and put them into the expression and get a number. Okay, so this one, we have, we're going to do products. This one's going to be a KP. So we have our products, which is BR2 raised to the 2 because we have a coefficient of 2. Does that make sense? So that squared comes from that coefficient in the front. And then we have water squared because we have this product raised to the 2 all over our reactants. So we have HBr raised to the 4 times, is that big enough? Hopefully. Oxygen raised to the 1. We don't need to put anything because it doesn't have a coefficient. Okay, we're seeing where we got that? Question so far? So that's the first step. Products over the reactants raised to the coefficients. And then the next step is I'm going to take these numbers, and instead of putting BR2, I'm going to put 83.7. I'm just going to read off. So I have this. I'm going to read off this and put it there. Okay.
It's just a step more than.
Yes, step more. I guess yes, step more than we already did. So instead of BR, I'm going to put 83.7 squared. Instead of water, I'm going to put 6.04 squared all over HBr. So 61.7 raised to the 4 times oxygen raised to the nothing, or not nothing, raised to the 1. Sorry, not nothing. Okay. And then I just type that in my calculator. Does that make sense? So let's find our calculator. Come here, calculator. Pop up yet? Okay, I know it's a little bit small. Oh, there's the calculator. Okay, let me see if I can put these numbers in right. So I've got parentheses 83.7 to the 2. And then that's going to be multiplied by 6.04 raised to the 2 parentheses, because I'm going to divide it. That's going to be on the top, and then this is going to be on the bottom. 61.7 raised to the 4 times by 79.8. Okay, and then we got this tiny number. Oh no, it's tiny, but we can put this in scientific notation. And then notice how many sig figs are given to me for all of these numbers. 3. So then this number can only have 3. So I'm going to put this here. 2.21 times 10 to the minus 4. Oh, okay. Okay, so then, just kidding. It told me to round to 2. So if it's different than the table, this is probably one on the test that's going to tell you. So this one is telling me it should be only 2. Oh, also, if that warning pops up, that means you have the right number. It just has the wrong sig fig. So that's a good sign. If you are going to get it wrong on the test, it will just mark it wrong. It won't warn you that you just had the wrong sig fig. Does that make sense? Okay. All right. Do you want to do another one like this, or are you good? What do you want to do? You're good? Okay. All right, so we've got that one done. The next one we're looking at is recognizing equilibrium from a sketch. Okay, so this one is a picture. I think the last 2 are pictures. Recognizing equilibrium from a sketch. So we have to remember that equilibrium, so we're still remembering that equilibrium, the equilibrium expression is our products over the reactants. This is important. If you can spell it, reactant. Okay. So this is a mixture. Like if we look in a microscope, we have an amazing microscope that can see a chemical reaction happening. Then we know that this is the reaction happening. So for this problem, our equilibrium expression would be these circles, the more Mickey Mouse looking one over the linear one.
Wait, so how do you know those each are the products?
Because this is the product.
Oh,
This is the product side. Yeah, this is the product side. This is the reaction side. Good question. That's important. And so I have products over reactants, and this has to be equal to 5 if this is at equilibrium. So when this is at 5, this reaction is at equilibrium. Sorry?
Is it supposed to be 10 divided by 10?
Oh, no, this is just a number. This is just 5. So this number over this number. If it's 5, that's at equilibrium. So let's go ahead and count up. How many of these ones do we have? 1, 2, 3, 4, 5. We have 5 of those. And we have how many line ones? 1, 2, 3, 4, 5. So we have 5 line ones.
So the one on the left is always on the bottom.
One on the left is always at the bottom, is the reactant, yes. So 5 over 5, what does that give us?
1.
So that gives us 1. I'm just going to write 1. That's 1. So it's not equal to 5, so it's not at equilibrium. Does that make sense? Okay, let's do the next one. So this is saying the blue thing. 1, 2, 3. So product over reactant, this more circly one. Oh man. No. Okay, can you tell? This one's red. Red. This one's blue. If you can't tell from my picture. So at equilibrium, it would be 3 over 2. So let's see what it actually is. So right now we have blue. 1, 2, 3, 4, 5, 6. Blue. And 1, 2, 3, 4 red. So if we simplify this, we could divide a 2 out of both of them. This one becomes a 3. This one becomes a 2. So is that true? This one is true. 3 over 2 is 3 over 2. So this one would be yes at equilibrium. Does that make sense? Okay. I'm going to do these last two. I'm not going to draw them. I'm going to say the gray one is on the top. The blue one is on the bottom because I have my products over my reactants. I have how many gray ones? 1, 2, 3, 4, 5, 6. I have 6 grays over 1, 2, 3, 4, 5, 6 blues. So my equilibrium, or excuse me, right now the reaction constant is 1. To be at equilibrium has to be 3 over 2. So this one would be not at equilibrium. Does that make sense? Okay. And the last one, products over reactants. So I'm going to call that one pink over golden. We'll just call it yellow. So there's 1, 2, 3, 4, 5, 6 pink ones over 1, 2, 3, 4 yellow ones. Products over reactants. This should equal 3 over 2 at equilibrium. So is this true? Yes. If we simplify this, divide by 2, divide by 2. This is also at equilibrium. Yes. Okay. Let me check. Questions on that one? So we did 4 examples. Do you think you could do that on your homework? Or do you want to do another one? We're good? Okay. Let's go over the last type of question. Predicting equilibrium composition from a sketch. So another sketch. Oh, lots of fun. Predicting. Okay, this one's a little bit confusing, but it's not too bad. So we're going to do the same thing again. So we've got products over reactants. Let me make that a little bit bigger. So we have our reactants and our products. They can interconvert. So when we're thinking about this problem, let me just get a new paper. For this problem, we only have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 things to work with. Okay. So right now we have 1 reactant and 9 products. Okay. So it has to be products over reactants if we're talking about an equilibrium expression. Okay. So right now we call that the reaction constant. Our reaction constant right now is products. We have 9 of those. Did I count right? Yeah. And we have 1 reactant molecule. Okay. So at equilibrium, it's going to be 1 over 4. So we need to figure out how many products and how many reactants in this picture. So how many products have to change to a reactant for it to be at equilibrium to get 1 out of 4? So 8.
Would be minus.
So you're saying that 8 needs to come here to go down here. So this is kind of tricky because you have to shuffle them.
So we're trying to get 9 to 1.
We're trying to get something. Yeah, it's like we have to get some of these 9 have to go down to the bottom so that we can get a 1/4 fraction. So if I think about this fraction, I need the top and the bottom of the fraction to add up to 10 because I only have 10 molecules. So I'm going to put 7 down here. So I'm going to put 7 of these are going to convert, and I'll end up with 8 reactants. Yes, and you can simplify it too. And I'm going to have 2 products. So I still have a total of 10 molecules, but there are 2 that are now products. And now there's 8 that are reactants. Does that make sense? Yeah. So then this would simplify to 1/4. And then the question is asking me how many products and how many reactants. And I don't like this question because they flip it. So we've been working with products on the top and reactants on the bottom. So when you put it in, you need to make sure, oh, they're asking for reactants here. I need to put reactants. That's 8. They're looking for products here. I predict that there would be 2 products at the equilibrium. Okay. So kind of watch out for that. I feel like they should either put them side by side or flip them to match our equilibrium expression. Okay, let's do another one of those. I think these are confusing to me because I have to think about fractions. Okay, so same thing again. So first, I like to figure out how many total molecules there are. So I've got my equilibrium expression, products over reactants. Here, the products are blue and the reactants are red. I'm not sure if they're always like that. Right now, we have blue products. 1, 2, 3, 4, 5 products. And we have 1, 2, 3, 4, 5, 6, 7 reactants. So we have a total of 12 molecules to work with. Okay. At equilibrium, we need a ratio of 1 product for every 5 reactants. Okay. So we need to shuffle some of these. So think about what fraction will give me at equilibrium, it's 1/5. Right now it's 5/7. So what if I take this and I multiply by 2? If I have 2/2, that would give me a ratio of 2 to 10. So could we do that? So then 2 plus 10 is 12. So if we move 3 of these down to the denominator, so we're going to move 3 from the top to the denominator, then we'll get a fraction of 2 out of 10. Does that make sense?
Wait, so mine is already 2/10, and I need to make it equal 4/5.
Yours is on. Yes.
So it just gave me already?
Maybe. That sounds weird. And then just make sure you put them in the right spot. So remember this one, they ask for reactants. Those are on the bottom of our expression. Products are on the top of our expression. Was that right?
Yeah.
Interesting. You didn't have to do anything. Nice. I hope you get one like that on the test. Okay. Does this make sense? Do you want to do another one? Or are you good? Where are we? Okay. We have, what time do we get out? Oh, we have 35 minutes of class left. So I'm gonna, if you don't want to do another one of these, I'll just let you have work time. Make sure that your pre-lab 3 is done. Make sure your pre-lab 4 is done.
Wait, so that's the